All right, let's start. So, hello everyone. Welcome all of you to the Warren lecture. So I'm very happy today because two things mainly. One is that we have our prospective graduate students here. So welcome to the Balmy, Minnesota in February. And the second thing I'm happy with is that I have the privilege to introduce my friend and colleague, Ian Jacobi. He's an associate professor at Technion University, which is the best engineering school in Israel, essentially. Ian and I met about 15 years ago at Caltech. I was a postdoc. He was a PhD student. We ran a glorious experiment with a soccer ball in a wind tunnel. That was just one-day experiment, unpublished. It got more press attention than any of all my published work. So let's try not to read too much into that. And then we interacted and we spent time talking at conference mostly on wall turbulence. So he's an expert in wall turbulence and fluid mechanics, so at the borderline between engineering and physics. He got his undergrad at MIT and PhD at Caltech. He was a postdoc at Princeton. And Ian, thank you very much for being here. The floor is yours. Thank you.
Thank you, Michele. So when people talk about turbulence, they usually assume that turbulent flows are random and chaotic. And if you looked at a snapshot of a turbulent channel flow, you might agree it does seem random and chaotic. But if you look more carefully, you notice that turbulence is actually really highly organized, that it's made up of very well coordinated, coherent structures that range a whole range of length scales, from very small scales up to very large scales. And the small scale coherent structures, people focus on them if they want to understand the energy dissipation in turbulent flows, or perhaps drag processes very close to a wall. But the large scales are also very important. They contain at least half the energy in turbulent flows. And these large scales, and when I say large scales, I mean scales that are multiple times the size of the geometry of the flow. So let's say you have a channel height or a boundary layer thickness. There are large coherent structures that are many times the size of those dimensions. And you could actually extract large scale features out of a flow. And if we isolate one of them, here's an example of a large-scale, high-momentum structure that you see it's coherent over, in this case, 8 times the boundary layer thickness. And you have these very large-scale structures in the turbulence, and they're quite important for a variety of reasons. They're important on theoretical level and also on a practical level. On a theoretical level, these large-scale structures are important, number one, because they tend to organize the small scales. And number two, if you want to do reduced order modeling of fluids, you often want to represent large coherent features. So this would be a basis for a lot of modeling efforts. On the practical side, these large-scale structures show up in all sorts of interesting physical phenomena. And since we're in civil engineering, I thought I'd give a few examples, one of which I can plug the department here and the work of my host, Michele. If you're interested in, for instance, looking at wind turbines and wind farms, you really have to pay very careful attention to the large-scale coherent structures downstream of a wind turbine, because that's going to affect the energy generation, it's going to affect the placement of other wind turbines, the whole design of the wind farm. And not only that, you also want to pay attention to the large-scale structures that are upstream, coming into the wind farm, that are natural in the atmosphere, because they're also going to have major impact on the energy generation. Similarly, these large-scale structures show up in all sorts of sedimentation and bed dynamics problems. So if you're interested in sediment transport, people often think about describing sediment transport as a result of secondary flows. You have a primary flow of the direction of the river, and then you have these three-dimensional secondary flows. These secondary flows can often be thought of as a consequence of these large-scale motions, that they're actually induced by large-scale motions. So a lot of bed form dynamics can be explained in terms of these large-scale motions. So then the question is, what would we like to know about large-scale motions in turbulence? And you could ask a couple different questions. We might want to know what the spatial structure is. What do these large-scale motions look like? How would we represent them? How would we model them? You also might wonder, how do they interact with the other scales, the other coherent structures in turbulence? How do they organize the small scales? And then you might want to know how these large scales move. How fast do they go? How fast are these large scales traveling in turbulent flows? And it's this final question that's really going to be the focus of my talk today. And it turns out that you have to know how fast these large scales are moving if you want to answer the other two questions. So we're going to focus on this question of what's the velocity at which these large scales move? Or in general, what's the velocity at which all these coherent structures move in turbulence? And this is really a very old question. It goes back to the 1930s. People started thinking about how you could represent the motion of all these coherent structures in turbulence. And the simplest possible assumption is to think that all these structures are just sort of frozen in a turbulent flow, and they're being advected along by some mean velocity. So that's the simplest way of thinking about it, and I can illustrate that with a little cartoon. So here are my three coherent structures. I have, circle, square, and a triangle, and they're being advected left to right in the streamwise direction, and I'll assume they're being advected with some advection velocity u sub c. So my x direction is along left to right, and I have a time axis from top to bottom. And then let's assume that I have some sensor in the field, and I'm going to measure my turbulence. And that sensor I'll put at position x naught. And of course, the sensor is going to be fixed in location. So on this little xt diagram, it's going to be represented by this gray line. It doesn't move in location. So as the flow is moving left to right, each one of my little structures passes my sensor, and then I'll record it in my little sensor box up there in the top right. So first, of course, I measure my triangle as that structure passes through, and then, of course, I'll measure the square, and I'll record that, and I'll measure the circle. So now I have this time series of all these coherent structures, and I really want to answer that first question. Well, what's the spatial structure of the turbulence? I only made measurements at this one single point, but I'd like to know what it looked like if I had a giant photograph of the turbulence. So how could I use that time series to reconstruct the spatial picture? Well, if all the spatial stuff is being advected with a constant velocity, and if I knew what that velocity was, if I knew what that uc was, I could just change that coordinate axis. I could multiply the time by velocity to get a spatial dimension, and I could subtract that from my measurement point. And if I do that, I can reconstruct a picture of what I think the spatial representation of my turbulence is. And lo and behold, it looks very much like the original picture, the snapshot that I started with. So this sort of reconstruction works great if the turbulence really is frozen, if nothing's happening to these structures. But of course, as you can imagine, these coherent structures in turbulence are evolving dynamically in time. And therefore, this isn't necessarily going to work so well if those structures are changing. So let's try this again, but this time let's allow for those structures to change and evolve in time. And I'll represent that change by a little bit of rotation. So at each time step, I'll have my structures rotate just a little bit. So now I record my rotated triangle, and then I'll record my rotated square. And it keeps rotating in time. So now I have my time series, and of course I'll play the same game. I'll use my convection velocity to change that coordinate axis so that I could reconstruct what I think the picture of the spatial turbulence looks like. But of course, you see, this doesn't match up with any of the snapshots at any given time instant, because my time series is really a combination of a bunch of different time snapshots, but it's never one time instant. And because each of those structures are evolving, I never actually get an accurate representation of the turbulence at one time instant. And this was also a well-known problem that C.C. Lin back in the 1950s pointed out, that if you have a time evolution that's happening very quickly compared to the spatial variation of your turbulence, then this frozen hypothesis is never going to work. So you have certain restrictions on when the frozen hypothesis works. So that's what happens if these little structures are evolving. But there's another problem that could come up. What happens if each of my structures has its own convective velocity? So instead of just one UC, now I have UC prime, double prime, triple prime. And if I assume that each structure is going perhaps faster than the other one, now what happens? Well, I can see that as time evolves, the structures are dispersing. Right? So one structure is winning the race. My triangle is going much faster than the square is going faster than the circle. And of course, when I collect all this in my time series, now if I try to do that same process and transform my time into a spatial domain, I see that my reconstruction is going to be totally distorted from the actual spatial picture. All right? So I'm not going to get an accurate view whatsoever. So the question is, does this actually happen? Is this a realistic idea that all those structures in turbulence actually convect at different velocities? And it turns out that in some very simple level, yes, it does. And you could imagine, for instance, if all of these structures in turbulence are growing up from the ground. So a really big structure has its feet on the ground and then extends very high up in altitude. And the smaller structures start from the ground and extend to smaller heights. If that's the case, so then these big structures have their center of mass very far away from the ground and are going to be advected much faster because they have a much higher velocity far from the ground as compared to some small structure where the velocity is going to be much lower. Now, what happens if I were out in the field and I were trying to measure this velocity field, and by measurement location were this black dotted line very close to the ground? Well, if that was the case, what would I see? I would see these large structures that look like they're moving much faster than the small structures because these large structures are actually part of this much bigger thing which has its center of mass far away. So in reality, what you do find is each of the structures in turbulence tends to advect at a different velocity. So now we have a problem if we want to reconstruct the picture of turbulence because each structure has a different velocity. So I need to know the velocities of all these different structures. Now, how could I know that? Well, if I had both the spatial picture and the temporal picture, then I could figure it out, right? If I knew the spatial picture of my little square and the temporal picture, I could infer what the actual convective velocity of that is, right? And if I have the spatial picture, many of you are probably used to seeing some sort of spectrum. I could construct the spatial energy spectrum of the turbulence, the distribution of how much energy is in all the different scales of turbulence spatially in terms of a spatial wave number. And if I had a temporal measurement, then I could do the exact same thing. I could look at how the energy is distributed across all the different structures in turbulence in terms of the different frequencies, omega. But if I had both of these pieces of information, if I had both the temporal and the spatial measurements, then I could construct a two-dimensional energy spectrum, which shows how the energy is distributed along omega in the time domain on the y-axis and along the wave number, the spatial domain, in the x-axis. And the interesting thing about this sort of two-dimensional plot is I know the relationship between frequency, wave number, and phase speed. In other words, it's just one divided by the other. And therefore, I would expect, based on this, that the slope of this plot should represent something like a phase speed or a convection velocity. So when I look at this spectral map, I see, yes, it's sloped very distinctly. And the slope of that actually corresponds to the velocity of the different structures. And in fact, this red line is the mean velocity for the particular location where these measurements are made. So you can see that the spectrum is very close to the mean velocity, although if I trace the peaks of this spectrum, the dominant velocities, that's the cyan line, you see it's not exactly on the red line, meaning for any given structure size that I want, I could choose a wave number, say K1, and I could figure out what's the dominant velocity at which that size structure is moving, and it's not necessarily going to be exactly the wave number. It's not going to be exactly the phase speed of the mean flow. Now, so if I was interested in just figuring out the dominant velocities, so this would be a great way of doing it. I could just trace along the peaks of this sort of map, and I could tell you what's the dominant velocity for every structure in turbulence. But that's not what I actually want to focus on. What I want to focus on is another feature of this plot, which is the fact that it has a certain width to it. There's a certain thickness. That means that for a given structure size, a particular wave number, there's a whole distribution of different convective velocities at which those structures are moving, not just one. And that's really important. If we go back to that wind farm example, if you're designing a wind farm, you don't just care about what the mean electrical energy output from the wind farm is going to be. You need to know about the fluctuations too, right? So therefore, you need to know the distribution of the phase speeds of these different coherent turbulent structures that are coming into the wind farm. So what I'd really like to know is what's that distribution? Now, it's a little hard to see on this plot because I'm still plotting in terms of omega and kx, but I could redo this plot in terms of the phase speed c by simply dividing omega by kx. And if I do that, I can transform this plot into a plot that shows the phase speed. Here, I've just normalized it by the local mean velocity, so it's going to be centered close to zero, not exactly zero. as a function of the wave number. And what we can see is, yes, indeed, there is a width to this distribution of phase speeds. For any given size, I can see there's a whole distribution. And I'd like to be able to predict what is the width of that distribution. How variable is the phase speed for a given structure size in turbulence? So I want to predict this. And the question is, to predict this, I basically have to predict the two-dimensional spectrum. How can I predict the two-dimensional spectrum? And it turns out that's also a reasonably old problem. Back in the 1960s, Technion proposed a very simple model to get the two-dimensional spectrum. The model is very elegant. He said, let's assume you have some small-scale turbulence, a little bubble of turbulence that's going to be advected. So these are all small scales, and they're being pushed around, and they're being pushed around by two things. They're being pushed around by some mean flow, capital U, and they're being pushed around by some other large-scale turbulence, which I'm calling little v here. This large-scale turbulence, I'm assuming, is isotropic, homogeneous. It has no spatial distribution, and therefore it doesn't really interact at all with the small scales. There's a huge separation between the large-scale turbulence and the small scales. So the small scales are just being swept along by this large scale, and that's what he calls this a sweeping model. So according to the sweeping model, I can model the small-scale turbulence being advected with a very simple advection equation. Right? Just take your Navier-Stokes equation and drop everything but the advection terms. I have the small-scale turbulence U that's being advected by two things, capital U, some mean velocity, and V, which is just going to be some number, has no spatial distribution. It just represents the intensity of all this isotropic homogeneous turbulence. So now I have this spatial advection equation, but how do I get a spectrum from it? Well, Technion had a wonderful trick. Take the Fourier transform of this equation in space. If I take the Fourier transform in space, I get rid of that x derivative, right? It becomes a wave number, kx. And now I've turned my PDE into an ODE. I can solve this ODE, right? So I can solve the ODE for u hat, which is the Fourier transform velocity, as a function of kx and time. And once I have that Fourier transform, I could construct a spectrum by taking that, multiplying it by its complex conjugate, ensemble averaging in the usual way. Now I have the spectrum as a function of wave number and time. And now I do another trick. Now I transform it one more time. I do a Fourier transform of the spectrum to convert that time into frequency. And if you do that, and there's a lot of math in between, which I'm going to spare you, but if you do that, you end up getting a two-dimensional spectrum in terms of wave numbers and frequencies. Exactly what you wanted to predict. Now, I actually wanted it in terms of phase speed, so I can rewrite this in terms of phase speed, c. But if I look at it in terms of phase speed, what is this function? It's just a normal distribution, right? This is just a Gaussian function. This is just telling me that my phase speed c is distributed around an average, which is the mean velocity, capital U, just like in my plot, centered around the mean velocity. And it has a variance that's based on the intensity of that turbulence v. And that variance, of course, since I said v was just a number, that variance is just constant. So if I look at my plot, I ask, well, is the width, is the variance, is the standard deviation of this distribution constant? And the width does look constant, at least for the higher wave numbers, the small scales. This model works great. It doesn't work for the large scales. When I get to the low wave numbers, there I see that the width of that distribution seems to vary. It gets wider and wider as I get to larger and larger scales, smaller and smaller wave numbers, but there's no kx dependence here. So I'm not going to be able to predict the variability of the large scales, and those are the scales that I want to predict if I'm going to be modeling my wind farm. So I need to figure out how to modify Technion's model. And it turns out the way to modify his model is to allow the turbulence to interact. Allow the large-scale turbulence in the V to interact with the small scale in U. And in order to allow that interaction, you have to make V no longer just some random number. Now it's going to have a spatial distribution X. It's going to have a shape, right? If V has a spatial distribution, now when I take the Fourier transform, I'm going to have two functions that depend on X that are multiplied together, which is going to give me this horrible convolution operation. And which means I can't solve the equation anymore. Like, what am I going to do with this convolution? So what I can assume to try to get around this messy convolution summation is assume that in my V, in that turbulence that's doing the sweeping, there's only one scale that really matters. Just one big scale dominates. So I don't need to have this whole sum over all the scales. I can just use one big scale. And if I represent the whole summation in terms of one big scale, which I'll call K sub V, that'll be the wave number for that one big scale. Now I have an equation which I can solve. It's still a lot of math to solve it, but I can essentially solve this the same way I did the previous Kreifman problem, and I can obtain the same sort of Gaussian distribution. This time, once again, my phase speeds c are distributed about a local mean velocity, but now the variance has kx dependence, and it has a kx dependence that's in the form of an inverse kx dependence. So as the wave numbers get smaller, my variance goes up and the distribution gets wider. And then I can compare, well, how good does this model do? Does this simple scale interaction model capture the trend? So I can go back to my original graph and I could figure out what is the standard deviation, what's the width of this distribution as a function of wave number, which is what I have plotted here in all these black and gray lines. And then the red line is the trend that you get from fitting this sort of model. So the first message that I have in this first segment of the talk is to tell you that if you want to model convection velocities, if you want to understand the variability of convection velocities, particularly for the really large scales in turbulence, you have to take into account scale interactions. If you don't allow the scales to interact, you'll always underestimate or you'll never accurately estimate the variability of convection velocities. Okay, so that's going in one direction, but my title said there were two problems. So the second problem, I want to go in the opposite direction. Here we started with convection velocities and then we went to scale interactions. Now I want to start with scale interactions. If the scale interactions are so important, how do we measure scale interactions, right? What can we say about scale interactions? And how is that eventually going to relate to convection velocities? So let's talk a little bit about how you might measure scale interactions. And one of the popular ways of thinking about scale interactions comes from just looking at the signals of turbulence. You went out in the field, you collected some time series, and you look at the instantaneous turbulence signal, and I want to see how the large scales and the small scales interact. So I'll filter that instantaneous signal into a large scale signal and a small scale signal. And then what I notice is that when you see this sort of negative deviation of the large scale signal, it seems like it's correlated with a decrease in the intensity of the small scale fluctuations. And when you have the positive variations of the large scale signal, it seems like it's correlated with an increased intensity of fluctuations of the small scales. In other words, it seems like the large and the small scales are correlated. Well, that might be good evidence for some sort of interaction between these scales. So people came up with a correlation coefficient, where they can actually do a correlation of the large scale signal and the envelope E of the small scale signal, the intensity of the fluctuations. And you can plot this correlation coefficient as a function of the wall normal distance, the distance up from the ground, we'll call Y. And you can see that the large and the small scales are highly correlated near the wall. They're oppositely correlated away from the wall. It crosses zero at some point in between. So this seems like a great way of thinking about interactions between large and small scales. But of course, we do have to ask the question, does R actually measure nonlinear interactions? R is a correlation. A correlation coefficient is really a linear operation. Does it actually capture the nonlinearity that we know is at the heart of turbulence? So we could ask the general question, how would we measure nonlinear signals, or how do we find nonlinear signals in any sort of experiment? Now, I talked about this at SAFL a few weeks ago, so I'll talk about it a little bit more now, which is if you're given some signals and you don't know whether they come from linear dynamics or nonlinear dynamics, how would you choose? How would you decide whether it's from linear or nonlinear dynamics? So we can play the little game. Here's round one of the game. Here are two signals that I made up. You have a green signal and a blue signal. Can you figure out which one comes from linear dynamics and which one comes from nonlinear dynamics? From visual inspection, it's a little hard. Maybe you'll say, well, this one looks a little more periodic. And if it looks more periodic, maybe it's less likely to be nonlinear. But of course, the first thing that I would do is I would just look at the spectrum. So I could calculate the Fourier transform. I could calculate the power spectrum of that green signal. And I'll see that it has two peaks, just two components, right? I can imagine this is like two cosines. And if these two cosines were interacting nonlinearly, if they were multiplied together, then I would expect, in addition to those two peaks, I might expect energy at both the sum and the difference wave numbers. That's like when you multiply two cosines, you'll get sums and differences. But here I don't see that. So maybe this green signal was just a simple summation, purely linear. And then I could look at my blue signal. It's like, oh, well, here, the blue signal, it's exactly what happens. I have my peaks at 2 and 3, but I also have 5 and 1, the sum and differences. So I might be thinking, well, okay, the blue signal, that's much more likely to be nonlinear than the green signal is. We could try the game again. Here's the same blue signal, and now I've added a red signal. And now we want to play the same decision. Does one look more nonlinear than the other? Is one of these linear or nonlinear? Hard to tell visually. We can look at the spectrum. And if we look at the spectrum, oh goodness, they're exactly the same. Isn't that disappointing? And if I tell you that one of these actually is nonlinear and one of them is linear, now we have a problem. Because how in the world are we going to decide which one is which based on the spectrum? You can't actually distinguish. Now, luckily, in this toy problem, I can just give you the answers, right? So let me give you the answers of what I was actually plotting in those plots. So the green signal, that was a simple linear superposition. Two cosines, one wave number k prime, one wave number k double prime, easy. The blue signal, which I was trying to make it look like it was nonlinear, it's also superposition. I've just added 4 cosines together. I just artificially added a cosine that has the sum and a cosine that has the difference of those wave numbers, and I put random phases, phi plus and phi minus on them. So this is going to look on the power spectrum like it's nonlinear, but there's no multiplication, there's no linearity at all. The red signal has the same 4 components as the blue signal, plus what I've circled here, a nonlinearity. Here I have the multiplication of the 2 cosines. And of course, if I were to do a trig identity and expand out that multiplication, it'll look very much like the sum and the differences. However, it won't be exactly the same, right? Because when I multiply these two, not only will I get the sum and the difference of the wave numbers, but the phases will also be summed or will have sums and differences. Whereas here I have random phases. So the only way to tell the difference between the nonlinear signal and the linear signal is to look for that phase coupling, because they're both going to have energy at the sum and difference wave numbers. But these phases, the phases that come from the nonlinearity, are going to be the result of interactions from the 2 other scales, whereas in the linearity, they're just random. So this is why using the power spectrum doesn't work, because the power spectrum only looks at 1 wave number at a time. But I can't look at 1 wave number at a time. I have to look at 3 wave numbers together. I have to look at the k prime, the k double prime, and then the sum to see whether the phases are all coupled together. So you'll never be able to find this sort of nonlinearity if you're only looking at power spectra. We need to look at 3 different components. So we can do that very easily. Here I've just rewritten my signals, but instead of writing them in cosines and sines, I wrote them in complex exponentials just to make the math easier. It's almost like I've written the Fourier series for you. And now I can pick out very easily the Fourier coefficients at the 3 wave numbers that I think might be interacting. The k prime, the k double prime, and then the sum, for instance. So for the blue signal, or linear signal, those Fourier coefficients are very simple. They're just based on the 2 phases, and then of course that random phase for the sum. In my red signal, the one that I know is nonlinear, of course I have the 2 initial phases, but now I notice in that third Fourier coefficient, I have a sum of those phases. So now I have to figure out, how should I put these Fourier coefficients together in a way that will reveal the phase coupling? In other words, I need to put them together so that the sum of these phases is equal to the 3rd phase if it's really non-linearly coupled. Or in other words, I want to subtract the 3rd phase from the first 2 phases to see whether that's 0 or not. And I can do that very easily. I could take my 3 Fourier coefficients and I can multiply them. That'll give me a sum of the first 2 phases when I multiply in the complex domain. And the 3rd one, I'll put a complex conjugate, a little star, and that'll give me a minus sign. So that'll be the sum of the first 2 phases minus the 3rd phase. And then I just have to average this over all my data, ensemble average. But of course, that 3rd phase for my linear signal is random. So on average, this is just going to come out to 0. So I'm not going to have any result here. So the linear phase, the linear signal is going to give me nothing in this diagnostic, which is exactly what I want because it's linear. I'm looking for nonlinearity. But the nonlinear signal, my red signal, now I have the sum of the phases from the 2 inputs. And then I also have the sum of those 2 phases with the minus sign from the output, from the nonlinearity. So when I subtract these, I'm going to get e to the I0, which is just 1. And when I do my ensemble averaging, that's going to remain. And therefore, I'm going to get some non-zero number in this case. So now I have a way, using spectra, to identify a nonlinearity. And of course, this fancy spectrum has a name. It's called the bispectrum. It depends on 2 different wave numbers instead of 1. And it's also, of course, a complex valued spectrum. So because it's a complex valued spectrum, the bispectrum has a magnitude, which when it's normalized, people call that the bicoherence. And it has the thing that we care about, which is this biphase. And when the biphase is 0, then I have my nonlinearity. So if I'm looking to identify nonlinearities, all I have to do is calculate the bispectrum and then look at the biphase to see whether it's 0. Okay, but that was only for one type of nonlinearity. That was for this simple multiplication. That was just a cosine times a cosine in my red signal. That's like a u squared. But in turbulence, and in fluid mechanics in general, we know the nonlinearity is not u squared. It's u dot grad u. It's a convective nonlinearity. That would be like making a signal where I have this extra spatial derivative, a ddx in here. Well, if I take this derivative of the cosine, that's going to turn one of my cosines into a sine, which is pi by 2 out of phase with the cosine. So when I do the analysis, my bispectral analysis, now I'm going to have that extra factor of pi by 2, which is going to show up. And through the ensemble averaging, I'm going to get that additional factor of pi by 2. So now I have to be very careful, because before I said the nonlinearity is biphase is equal to 0. But that's only for a quadratic nonlinearity. But if you have a convective nonlinearity, the biphase is going to be negative pi by 2. Okay? So now we have a way of identifying nonlinearities. And in particular, we have a way of identifying nonlinearities in turbulence or in fluid mechanics more generally. And now, of course, the question is, what in the world does this have to do with R? I started by telling you that the large scales are coupled with the small scales because we can see that they're correlated. Right? And I said that there's this correlation coefficient. And I asked, does the correlation coefficient really measure nonlinearity? Well, now we have the tools to measure nonlinearity. So the question is there any relationship between R and the way of measuring nonlinearity? Well, I can actually write R in a spectral form, because R is just made up of these velocity signals. So I could write the Fourier transform of my velocity signal as a Fourier series. And then if I want the large scale signal, well, I can filter that. I can just leave out of my summation some of the higher wave numbers. And if I want my small scale signal, I can also leave out different wave numbers. And I can create an envelope by simply squaring those signals. And I can basically write all of the components of that R in a spectral form. And then I can plug them all into R, and I can do a bunch of math. And this is what you get. You get that R has some normalization, it has a bunch of summations, and then it's the real part of this funny spectrum. And this spectrum is, of course, the spectrum we just saw, the bispectrum. Well, isn't that amazing? This is terrific news, right? The R, which we hoped was measuring something about the nonlinearity, is related directly to the one tool that I showed you definitely measures nonlinearities in turbulence. It's the real part of the bispectrum. So I can actually rewrite this as a real part of the bispectrum. So now I have the magnitude of the bispectrum and the cosine of the biphase. So all I have to do is plug in the biphase that I expect from turbulence. And that biphase was pi by 2. But if I plug in pi by 2 or minus pi by 2 into cosine, I'm going to get 0, right? In other words, if R is measuring the nonlinearity, R should be equal to 0. R can't measure the nonlinearity. But R isn't equal to 0. I showed you the graph of R. R was only 0 one location. R is basically not 0 everywhere else. So R is measuring, if it's measuring the nonlinearity, it should be 0 everywhere. R must be measuring something else besides just nonlinear interactions. So it's not measuring what people thought it was measuring, but it is measuring something. So how do we figure out what R is measuring? Well, we can do a little bit of a toy model to figure that out. I can put together the convective term from the Navier-Stokes equations in spectral form. So if you look in any textbook, you can always write the whole transform Navier-Stokes equations. I'll leave out all the diffusive and pressure terms. I just have the convective term. And I see, of course, that convective term has this convolution operation. That's from the u dot grad u. That multiplication in spectral space becomes convolution. And I can use this to construct two different types of scale interactions in a very simple model to try to figure out what that R is measuring. Now, the first scale interaction I'm going to consider is just a regular nonlinear interaction. I'll have a wave number k, which interacts with two other wave numbers, k prime and k double prime. So this is just some large scale that's interacting with a bunch of smaller scales in the flow. And I can plug that into my formula, and I can write a simple expression that this represents that interaction. Now, if this was the only interaction in my system, I've already showed you that the biphase is going to be equal to pi by 2, and therefore R is going to be equal to 0. R is not equal to 0, so I have to include something else. So I'm going to include one more interaction. I'm going to assume that that same wave number k, that same large scale motion, also interacts with something with wave number 0, which is the mean flow. That's a linear interaction. That's not nonlinear. So I'll have one nonlinear interaction. The large scale interacts with small scales. And then that same large scale simultaneously has an interaction with the mean flow. And I can write the equation for that. Now I can solve both of these differential equations, again, with a little bit of tedious math, in order to calculate what these Fourier transform quantities are. And if I calculate what the Fourier transform quantities are, I can then plug them in to the bispectrum, and I can actually calculate the bispectrum. So this is what the bispectrum looks like for that model where I have both the large scales and the small scales, both the large scale interaction with the small scales and the large scale interacting with the mean flow. So I look at the biphase, and I can see in the biphase that, of course, I get that negative pi/2 again. That's from the interaction between the large scales and the other scales. That's from the nonlinearity. That's what I expected. But I also have this phi0 term, right? I also have, in addition to that, an additional contribution due to the interaction with the mean. And I can write out what that phi0 term is. And it turns out that that phi0 term depends on the wave number, how big the scale is. It depends on some time constant, which has to do with how we essentially discretize the equations in order to solve them. And it also has to do with u hat of 0. Well, the Fourier transform at wave number 0, that's just the mean velocity. And in fact, in this case, it makes a lot of sense to interpret this in a moving frame of that large scale, since everything was talking about the large scale interacting with the small scales, the large scale interacting with the mean flow. So if this represents the mean velocity in the moving frame, it really represents the difference between the local mean velocity and the velocity of the scale. Right? It represents, in some sense, the violation of that frozen turbulence hypothesis we started with, that the scale velocity, the velocity of that k wave number, is not exactly the same velocity as the local mean. The difference between them will affect the value of phi naught. And it turns out that when the scale, this k scale, is moving faster than the local mean, like it does near the ground, near the wall, then you end up getting an R that's positive. And when this large scale is moving slower than the local mean, which is what happens very far away from the wall, then you end up getting an R is equal to negative. R is on the negative side. So this original plot that everybody assumed was measuring scale interactions, because after all, it measures the correlation between the large and the small scales. Where else would that correlation come from? It must be coming from scale interactions, and it turns out it can't be coming from scale interactions, mathematically speaking. It has to be coming from interactions with the mean flow. And therefore, what you're really looking at when you're looking at this correlation is another measure of the effect of differences in convective velocities. So just to summarize the two little short stories that I told you today. So the first story was a story of how you want to predict the variability of convection velocities, and you can't do that unless you very carefully take into account nonlinearities, because the nonlinearities can drastically affect the convection velocities. The second story, the opposite story, is how it's very easy to mistake correlations for the effect of nonlinearities when it's really just convection velocity effects in disguise. And you have to be careful on the opposite end to make sure that when you think you're measuring interactions between scales, it might really just be the difference between one coherent structure and the mean velocity at which the surrounding flow is advecting. So both of these pieces of work were mostly done by my postdoc, Guangyao Cui. So I have the citation. So I thank him for all the work that he did to try to explain these two problems. And I thank you for your attention.
Thank you. Thank you very much. Question?
I need to press on anything, or I just talk in it? I've never. Okay. Okay. Thanks for a really nice talk. I have what might be a really practical question. It might be a naive question. And it's from the first part of the story. It has to do with you picking out the large scale versus the small scale variabilities or vortices is the way that I saw it, and kind of going to the practical simplified version. If you have a regular channelized flow, we have turbulence of a range of scales. It seems to me that it is really useful to, if I understand you correctly, to understand the big scale and how they affect the little scale. How do you decide what to call the big scale? Like, it seems like you're taking, in the grain size distribution world, like a D85 and a D35, or something like that. And then on top of it, do you not just pick one, but you kind of, by picking one temporarily, then you sum over a range of it somehow?
Yeah. So in the model, when I showed this, I sort of skipped over the details
Yes.
of what is that wave number.
Yep.
I said I can represent the large scales by one wave number, and what is it? So it turns out that a lot of work in canonical flows have shown that certain particular large scale motions, what they call the VLSMs, the very large scale motions, that have wavelength 6 delta, 6 times the boundary layer thickness, something in that range, possibly even 10 or bigger, that those tend to be very significant in terms of organizing the flow. And we can actually show that going back to that correlation coefficient. If you write that correlation coefficient in spectral space in terms of different wave numbers, you see that most of the contribution to that comes from one very narrow range of wave numbers. Right. So what we chose to make this plot and to fit that red line, it wasn't just sort of a random fitting. We actually specifically chose a wave number that's the well-documented center of these very large scale motions. And that's what actually produces the fit. Now, that's to say that we do think that these large scale motions are dominant. The fit here is consistent with what other people found, but you're never obviously going to have one large scale. But it turns out that that's a good estimate for where's the dominant large scales in terms of predicting this variability. It's those very specific large scale motions that are many times the boundary layer thickness or many times the channel height. And yeah.
Oh, so, right. I was thinking that it might be the channel height or the channel width, but you're saying it's actually many times that.
Many times that, yeah. So at least, I mean, the numbers here, I think was 6, which is a sort of the standard, one of the standard peaks for the large scale motions is assumed to be around 6 times the boundary layer thickness or channel half height, but somewhere around there, but much bigger than the channel itself. Those are the ones that seem to have the dominant organizing effect on all the smaller scales in the flow.
Okay, and then there's and again, this might be the naive part. Now that I feel good about knowing that there was a single large scale, is there a single small scale, or do you just kind of figure out how to do the math for one small scale effectively, and then and that represents the physics for that one small scale, and then you sum it or integrate it, and then where do you cut that choice off if that's the way you do it?
So it turns out that the range of small scales is quite substantial, as you can see, right? I mean, so, and again, this is not even a log plot. So here we have a very wide range of these small scales. And when people refer to small scales, both in the correlation world and in this problem, it's usually scales that are just smaller than whatever that channel height is. So those are not exactly what people would think of as small scales. Right. Normally you think of small scales like things that are dissipative, but right. It could be that small scales are what you could call relatively small scales or smaller scales. And they're not really very small scales, but there seems to be a huge range of these smallish scales that are organized by these large scale motions. And you don't actually have to target just the smallest dissipative type scales. So this tends to work for a wide range of small scales. You don't have to make that choice.
So you don't make the choice. You just kind of choose one that's a little bit smaller than the big ones. Okay, interesting. Yep. Thank you.
Is the vertical dashed line in the second part where R is equal to 0, is that like a critical layer of like the large scale? And how is that related to like the—
You're talking about these plots there?
No, the second part of with the correlation where R is equal to 0.
Oh.
That's like the critical layer of like the K that you chose.
Yeah. So
okay.
So the R where the R equals 0. So there's been a lot of dispute for a long time about what's the significance of that R is equal to 0, because in the old interpretation, when this was interpreted to mean scale interactions, then R was often interpreted just like any cross-correlation coefficient. It's basically a dot product, and therefore it's a cosine of some phase difference. So when it was equal to 0, the assumption was that was a place where the large and small scales were sort of out of phase by pi by 2. Unclear what that means spatially, temporally, doesn't really, it's unclear. And it tended to be that this zero crossing would show up in the middle of the log layer. And people didn't really understand why would it show up in the middle of the log layer, but that tended to be empirically where it showed up. Now, according to our hypothesis, that R, what's really showing is the convective velocities. So when R is equal to 0, that means that the large scales are moving at the local mean. So there is this place in the middle of the log layer where the large scales are sort of at home and they're moving at the local mean velocity. And below that, they're moving faster, and above that, they're moving slower. So we think that we actually have a reasonably physical interpretation for that. And the previous interpretations, there are a variety of them, but they're a little bit shakier, I think, in terms of providing a simple physical interpretation.
Thank you.
My question is inspired by the problem of waves in condensed matter, which I know a little bit more about. So when you were showing the frequency versus wave number curve, so notwithstanding the slight difference between the red curve and the cyan curve, which seemed to be a little bit marginal, it seems like that the slope was constant. So we say constant group velocity. So all the frequency travel with the same speed. Is that a canonical scenario in fluid mechanics, or are there fluid mechanics scenarios where the heterogeneity, say, of the flow or something would give some curvature to that curve?
I mean, you see, the only place where I've seen lots of examples of curvature in that is in the magnetohydrodynamics type world, which I don't have real expertise in, but I have seen people discussing that in terms of the context of group velocities. In the paper, the original paper that discussed the convection velocities, Del Alamo and Jimenez from whenever it was, 2009 or 10, they also discuss the differences between the group velocities and the phase speeds. I don't think they came to any clear conclusions on that. The reason why the cyan and the red lines were so close together on that particular plot was because that plot was actually very close to the middle of the log layer. So if I would have chosen something much closer to the wall, then you would see more significant differences in the large scales and similarly farther away from the wall. So that's just sort of an artifact of the fact that everything that I presented is close to the middle of the log layer.
Any other question? Okay. Yeah, sorry. Can read it.
Or is it a
Yeah.
Okay. Judy Yang is wondering how you think energy dissipation might impact the results. Also, do you think the homogeneous assumption still holds when there is a separation of scaling?
Well, so to answer the second one first, we don't think that the idea of homogeneity makes any sense. And that's why we incorporate V, we write V as a function of X, right? So that's basically saying that it has some spatial variation. And therefore, we're saying that the scale separation and the homogeneity both basically have to fall apart in order to account for the scale interactions. So that's the thing I can definitely speak to. In terms of the dissipation, like I said, we don't really focus on the very smallest of the small scales. So it's a little hard to say, at least I can't say anything intelligent, I think, about what the role of those dissipative scales is in this process.
All right, I have one last question, and it's triggered by the sweet spot. So this is the spot in the log region where large scale motion, very large scale motion have been observed to have most of the energy.
Right.
So it's not a case then, because if they are advected by the mean velocity, they're not stretched too much. So it's a good space for them to evolve.
Right, exactly. So like I showed in that original cartoon with the dispersion,
Yeah.
right? The farther you are, the more different velocities you have for these large scales, the more dispersive they are. Especially if you think that these very large scale motions are a superposition of a
Yeah.
bunch of small scales that each might have their own velocities.
Okay.
So they're going to disperse much more quickly if they're all traveling at different velocities. Whereas if they're all moving at roughly the same velocity, at the mean velocity, then they'll stay together for much longer. You'll see much less dispersion. So one way you could check this perhaps would be to try to measure the lifetimes of some of these large scale motions. And you could show that how long it stays coherent is some measure of how dispersive it is. And if you could show the lifetimes as a function of wall normal height, that might be a way of sort of substantiating this.
Another way is to look at the very stratified turbulence, very stratified boundary layer, because then you don't have this interaction at the wall. And so you can actually prove the other way around when you lack that interaction.
Yeah, absolutely.
Very nice. All right. So thank you very much. And thank you all for staying.